Before the beaches were secured and before ports could be rebuilt, an unusual vehicle began emerging from the waves alongside soldiers and landing craft. It looked like a truck, moved like a boat, and forced both Allied planners and German defenders to rethink how war could be supplied from the sea. Crews drove straight into surf filled with obstacles, uncertainty, and enemy fire, never fully sure if the machine beneath them would hold together. Some saw it as a breakthrough in amphibious logistics. Others saw a dangerous experiment pushed too far by necessity. What followed was not just a story of innovation, but of risk, doubt, and the fragile line between engineering ambition and survival on open water. A truck that was not meant to swim, and the engineering doubts behind the DUKW. The idea sounded unreasonable at first. Take a standard military cargo truck, seal its body, add a propeller, and send it directly from ship to shore through open surf. Many engineers initially questioned whether such a machine could survive real combat conditions. Yet, the vehicle that emerged, the DUKW amphibious truck, was born from urgency rather than certainty. It was not designed because someone wanted a novelty. It existed because Allied planners faced a logistical problem that traditional landing craft could not fully solve. Early in the Second World War, American forces realized that amphibious assaults required more than infantry and tanks. Supplies had to move immediately from ships offshore to troops advancing inland, even when ports were destroyed or inaccessible. Conventional trucks could carry large loads once ashore, but they could not cross water. Small landing craft could reach the beach, but unloading them created delays that slowed the flow of ammunition, fuel, and medical supplies. The DUKW was conceived as a hybrid answer, yet the concept challenged established engineering assumptions. At its core, the vehicle was based on a modified GM-CCCW six-wheel drive military truck. Designers did not start with a clean sheet. Instead, they adapted an existing chassis and drivetrain to save time. This decision introduced doubt from the beginning. Trucks were built to handle uneven roads, not waves and saltwater corrosion. Transforming a land vehicle into a seaworthy platform required sealing mechanical components, reshaping the hull, and adding a marine propulsion system. Critics argued that combining these roles would produce a machine that performed neither task well. Buoyancy calculations became a central concern during development. Engineers had to ensure that the vehicle would remain stable while carrying heavy cargo loads. If overloaded, the DUKW risked taking on water or losing balance in rough surf. Early tests revealed that weight distribution was critical. Cargo stacked too high or unevenly could make the vehicle top-heavy, increasing the chance of capsizing. This forced designers to impose strict loading guidelines, yet wartime conditions rarely allowed perfect adherence to technical limits. Another point of skepticism involved steering and control. On land, the vehicle relied on traditional wheels and a conventional steering system. In water, it used a rear-mounted propeller and rudder, creating an entirely different handling dynamic. Transitioning between these modes required coordination from the driver, especially when waves pushed the vehicle sideways during beach landings. Some military planners doubted that ordinary truck drivers could adapt quickly enough to operate safely under combat pressure. Mechanical reliability also raised questions. The addition of a propeller shaft and waterproofed systems increased maintenance complexity. Saltwater exposure threatened engines, electrical components, and structural seams. Engineers attempted to mitigate these issues through sealing techniques and drainage systems, but field conditions remained unpredictable. During early evaluations, some officers worried that widespread deployment might lead to high failure rates once vehicles encountered real ocean environments. Despite these concerns, the urgency of amphibious operations accelerated production. Allied planners faced upcoming operations that required rapid logistical solutions, and delays were unacceptable. Testing continued even as manufacturing began, meaning the DUKW entered service while still undergoing refinement. This approach reflected wartime realities. Perfection was less important than functional capability delivered quickly enough to support major offensives. Initial reactions from troops were mixed. Some drivers viewed the vehicle with suspicion. unsure whether a truck designed for roads could truly survive heavy surf. Others appreciated its versatility once they saw it move directly from water to land without unloading cargo. Training programs had to address both technical operation and confidence building. Drivers learned to read wave patterns, manage throttle carefully, and maintain momentum while climbing beaches, all skills that differed from traditional trucking experience. Engineering debates did not end once the DUKW reached operational units. Discussions continued within Allied Command regarding its long-term reliability and safety. Some officers believed the vehicle represented a breakthrough in amphibious logistics, while others saw it as an improvisation that carried inherent risk. Reports from early deployments highlighted both successes and near failures, reinforcing the sense that the design existed on the edge of practicality. The doubts surrounding the DUKW were therefore not signs of failure. They were reflections of the unusual challenge it attempted to solve. Combining land mobility with seaworthiness forced engineers to compromise, balancing durability against buoyancy and simplicity against versatility. The vehicle was never meant to be a perfect boat or an ideal truck. It was a calculated response to a logistical gap that conventional equipment could not fill. What made the DUKW remarkable was not that it eliminated risk, but that it operated effectively despite widespread skepticism. Engineers accepted trade-offs that would have been unacceptable in peacetime design. Military planners deployed a machine many considered experimental because the strategic need outweighed uncertainty. The amphibious truck entered history not as a flawless invention, but as a bold attempt to turn an ordinary cargo vehicle into something capable of crossing the boundary between sea and land under the most demanding conditions imaginable. Normandy surf conditions and the near failures during the first landings. When Allied forces approached the beaches of Normandy in June 1944, planning collided with an uncontrollable variable: the sea. Tides, wind, and surf conditions transformed carefully calculated logistics into a gamble measured in seconds and meters. For the DUKW amphibious truck, Normandy was the first true test of whether an amphibious cargo truck could survive combat landings under hostile fire and unpredictable water conditions. What unfolded during the first landings exposed how close the system came to failure. The Normandy coastline offered no natural shelter. Waves broke unevenly, currents shifted constantly, and underwater sandbars altered depth without warning. DUKW crews launching from transport ships had to time their approach carefully. Entering the surf at the wrong angle could push the vehicle sideways, allowing waves to strike the hull broadside. Once that happened, recovery was difficult. Several early landings demonstrated how quickly a loaded amphibious truck could lose stability when waves exceeded expected height. One of the most serious problems was overconfidence in pre-invasion sea condition forecasts. Planners anticipated moderate surf that would allow controlled beaching. In reality, wind and tidal variation produced rougher seas than predicted. DUKWs carrying ammunition, fuel, and artillery shells were especially vulnerable. Heavy cargo lowered freeboard, leaving less margin between the waterline and the hull openings. Even small waves could send water over the sides, stressing bilge pumps and forcing crews to react instantly. Mechanical limits became visible almost immediately. The DUKW's propulsion system was sufficient in calm water, but rough surf demanded constant throttle adjustments. If engine power dropped during a wave impact, the vehicle could lose forward momentum and begin drifting. Several trucks were pushed off course or forced to abort landings after taking on water. In some cases, crews had to jettison cargo to regain buoyancy, sacrificing supplies to avoid sinking entirely. Beach obstacles further complicated the landings. Anti-invasion defenses included steel hedgehogs, wooden stakes, and submerged barriers designed to damage landing craft. While DUKWs could maneuver more freely than larger vessels, they still faced hazards beneath the waterline. A collision at the wrong angle could puncture the hull or jam the propeller. These risks were magnified by limited visibility caused by spray, smoke, and incoming fire. Human factors played a critical role in near failures. Many drivers were experienced truck operators but relatively new to amphibious navigation. Under combat pressure, they had to judge wave timing, maintain engine speed, and steer through surf while avoiding obstacles and enemy fire. Mistakes were costly. Hesitation at the surf line allowed waves to build, while excessive speed risked slamming the vehicle into shallow sand or defenses. Training could prepare crews only so much. Normandy demanded improvisation. Enemy fire intensified the danger. German coastal defenses targeted the beaches with artillery and machine gun fire. Although DUKWs were not primary targets, their movement made them visible. Crews often continued driving while under fire, unable to stop without risking flooding or immobilization. Damage to hull seams or control surfaces increased the chance of water ingress. In several cases, vehicles reached the beach only barely afloat, requiring immediate unloading and withdrawal. Despite these challenges, many DUKWs succeeded. Their ability to bypass congested beaches and deliver supplies directly to inland points proved invaluable. However, success did not mean smooth execution. Reports after the landings noted significant losses due to capsizing, flooding, or beaching failures. Commanders acknowledged that small changes in sea state could have resulted in far greater losses, potentially disrupting the supply flow during the critical first days of the invasion. Lessons were learned quickly. Loading limits were adjusted more strictly. Crews were instructed to stagger landings and approach at angles that reduced lateral wave impact. Communication between ship crews and DUKW drivers improved, allowing better timing of launches. These adjustments reduced losses in subsequent operations, but they did not erase the risks revealed on D-Day. Normandy demonstrated that amphibious logistics depended as much on environmental tolerance as on engineering design. The DUKW had been built to bridge sea and land, but the surf exposed how narrow that margin truly was. The vehicle functioned not because conditions were ideal, but because crews adapted under pressure. The near failures of the first landings revealed a fragile balance between capability and catastrophe, showing that even successful innovations could come dangerously close to collapse when theory met the open sea. Overloading, capsizing, and the mechanical risks crews faced at sea. The DUKW amphibious truck was designed to solve a logistical problem, not to operate as a true ocean-going vessel. Yet, wartime urgency often pushed it far beyond its intended limits. As amphibious operations expanded across Europe, crews faced growing pressure to move more cargo in fewer trips. Overloading became a frequent issue, and with it came a series of mechanical risks that threatened both the vehicle and the lives of those inside. Cargo planning manuals specified strict weight limits to maintain buoyancy and stability. In theory, a properly loaded DUKW sat low in the water, but remained balanced enough to handle moderate waves. In practice, conditions rarely matched those ideal assumptions. Ammunition crates, fuel drums, and artillery shells were often stacked quickly during chaotic loading operations. When cargo exceeded recommended weight or was distributed unevenly, the vehicle's center of gravity shifted upward, making it more vulnerable to rolling or taking on water during wave impacts. Capsizing risk increased significantly once the vehicle entered rough seas. Unlike purpose-built landing craft, the DUKW had relatively shallow sides. Waves striking at an angle could push the hull sideways, especially when cargo weight prevented rapid steering corrections. Reports from Allied operations described vehicles that survived heavy surf only to tip when turning too sharply or encountering sudden swells. Recovery was extremely difficult once a truck began rolling. In many cases, crews had only seconds to abandon the vehicle before it overturned. Mechanical strain accompanied these stability issues. Overloading placed additional stress on suspension systems designed primarily for land travel. While wheels provided traction on beaches, they added weight and drag in water, forcing the engine to work harder to maintain speed. Prolonged operation under heavy loads increased the likelihood of overheating or mechanical failure. Drivers had to balance throttle carefully, maintaining enough power to push through waves without overstressing the drivetrain. Water intrusion represented another constant danger. The DUKW relied on bilge pumps to remove water that entered the hull during operations. When overloaded, the vehicle rode lower in the water, allowing more spray and wave wash to enter through seams and openings. If pumps became clogged or damaged, water could accumulate rapidly. Crews were trained to monitor bilge levels constantly, yet in combat conditions their attention was divided between navigation, enemy fire, and maintaining formation with other vehicles. Propeller vulnerability added to the mechanical risks. The rear-mounted propulsion system functioned effectively in open water, but remained exposed to debris, obstacles, and shifting sandbars. Overloaded vehicles struggled to maneuver quickly enough to avoid hazards. A damaged propeller could leave a DUKW stranded between ship and shore, where waves and currents posed immediate threats. In some instances, vehicles had to be towed back to safety or abandoned entirely when propulsion failed. Human endurance played a role in these challenges. Drivers and crew members operated under physical strain, often exposed to cold water, heavy spray, and continuous engine noise. Long hours increased fatigue, making it harder to judge loading balance or respond quickly to sudden shifts in weight. Decision-making became more difficult when crews faced pressure to deliver critical supplies despite worsening sea conditions. Despite these dangers, operational demand rarely slowed. Commanders relied on DUKWs to maintain supply flow during periods when traditional ports were unavailable. The urgency of delivering ammunition or fuel sometimes outweighed strict adherence to loading limits. This created a cycle where vehicles were pushed beyond safe parameters, increasing wear and raising the likelihood of accidents. Maintenance teams worked continuously to repair damage, yet the pace of operations left little room for extended downtime. Engineering adaptations attempted to reduce risk. Crews received improved training on cargo distribution and were encouraged to secure loads tightly to prevent shifting during waves. Maintenance procedures emphasized checking hull integrity and pump systems before each mission. Even with these precautions, the fundamental challenge remained. The DUKW was a compromise between truck and boat, and overloading exposed the limits of that compromise. At sea, the difference between success and disaster often came down to small decisions. A few extra crates stacked too high could turn a routine crossing into a dangerous struggle for balance. A slight delay in adjusting engine power might allow a wave to break over the side. The mechanical risks crews faced were not abstract engineering problems, but immediate threats that demanded constant awareness. Overloading and capsizing incidents revealed that amphibious logistics carried hidden costs. While the DUKW expanded Allied capability by delivering supplies directly from ship to shore, it also introduced vulnerabilities that required discipline and restraint to manage. Each mission forced crews to navigate a narrow margin between efficiency and safety, reminding them that innovation at sea could be as fragile as it was essential. German confusion, coastal defenses, and the unexpected impact of amphibious trucks. When Allied amphibious operations intensified across Western Europe, German coastal planners expected landing craft, barges, and armored vehicles to form the backbone of any assault. What they did not anticipate in large numbers was a steady flow of amphibious cargo trucks moving between ships and beaches. The arrival of the DUKW amphibious truck created a logistical pattern that disrupted established defensive assumptions, forcing German units to adapt quickly to a vehicle that blurred the line between supply transport and amphibious landing craft. German coastal defenses were originally structured around fixed firing zones aimed at predictable targets. Heavy guns focused on larger vessels, while machine guns and smaller artillery protected beach obstacles against infantry and conventional landing craft. The DUKW did not fit neatly into these categories. It presented a smaller profile than many landing vessels, yet carried enough cargo to sustain advancing forces. Its ability to leave the water and continue inland without unloading created confusion among defenders who struggled to determine whether the vehicle should be treated as a primary target or a secondary logistical asset. Early encounters revealed how unexpected this capability was. German observers sometimes mistook the amphibious trucks for damaged landing craft or improvised vehicles rather than a coordinated part of Allied logistics. By the time the role of the DUKW became clear, The trucks were already moving supplies beyond the immediate shoreline. This reduced the effectiveness of defensive fire intended to delay Allied resupply, allowing troops to receive ammunition and equipment faster than anticipated. Coastal defense doctrine began to adjust as reports spread through German command channels. Anti-aircraft guns and mobile flak units were repositioned closer to beaches to engage low-profile amphibious vehicles. Machine gun nests that had been aimed toward infantry advances were sometimes redirected toward supply routes used by DUKWs. However, these changes required time and coordination. The dispersed nature of Allied landings meant that German units often reacted locally rather than through a unified strategy. The presence of amphibious trucks also complicated obstacle planning. Many beach defenses were designed to damage larger landing craft or prevent tanks from reaching shore. The relatively narrow profile and wheeled mobility of the DUKW allowed it to maneuver between obstacles or exploit gaps created by tides. Even when barriers slowed progress, the vehicles could attempt alternative routes along the shoreline, something less flexible craft struggled to achieve. This forced German engineers to reconsider how to block not just large vessels but smaller amphibious transports as well. Psychological factors played a role in the confusion. Defenders, expecting a pause between waves of landing craft, instead witnessed a continuous flow of vehicles emerging from the water. This steady movement suggested a level of logistical resilience that challenged assumptions about how long Allied forces could sustain operations without functioning ports. Reports from German units described surprise at how quickly supplies appeared behind advancing Allied troops, indicating that the DUKW contributed indirectly to the perception of overwhelming Allied momentum. German countermeasures evolved as the war progressed. Artillery units attempted to target known launching areas offshore, while reconnaissance aircraft searched for concentrations of amphibious vehicles. Some coastal defenses shifted toward area denial rather than precise targeting, using scattered fire to disrupt movement rather than focusing solely on large ships. These adaptations increased the danger for DUKW crews, particularly when operating in narrow approach corridors where defensive fire could be concentrated. Despite these adjustments, the amphibious truck retained an element of unpredictability. Its dual role as both watercraft and land vehicle made it difficult for defenders to anticipate movement patterns. A vehicle that appeared to be retreating into the surf might return moments later carrying fresh supplies. This flexibility complicated German attempts to time counterattacks or exploit perceived logistical pauses. The DUKW did not replace traditional landing craft, but it filled gaps in ways that forced defenders to divide attention across multiple types of targets. Allied commanders recognized the indirect tactical value created by this confusion. Even when individual DUKWs were damaged or lost, the broader effect on enemy planning helped sustain offensive momentum. Continuous resupply reduced delays between assault waves, allowing Allied forces to push inland before German units could fully reorganize their defenses. The amphibious truck became more than a transport tool. It became part of a system that reshaped how the shoreline functioned during combat operations. The unexpected impact of amphibious trucks lay not only in the cargo they carried, but in how they disrupted expectations. German coastal defenses had been built around known threats, yet the DUKW introduced a new logistical rhythm that was harder to counter. Its presence forced defenders to rethink targeting priorities, reposition weapons, and adapt strategies under pressure. In a war defined by large-scale planning, the sudden appearance of a vehicle that could cross water and land without pause revealed how innovation could alter the battlefield in subtle but significant ways. Supplying armies without ports and the dangerous logistics behind beach operations. In large-scale amphibious warfare, the capture of a functioning port was rarely immediate. Bombardment, demolition by retreating forces, and heavy fighting often left harbors unusable for weeks. During that critical gap, armies advancing inland still required fuel, ammunition, medical equipment, and food at a pace that traditional landing craft alone could not sustain. The DUKW amphibious truck emerged as a key tool in bridging that logistical void. moving supplies directly from ships offshore to units fighting beyond the beaches. Yet, the system that made this possible was far from safe. To amphibious vehicles using cranes or nets, while both the ship and the DUKW moved with the sea. This process exposed crews to falling cargo, swinging loads, and sudden shifts in weight that could destabilize the vehicle before it even began its journey toward the shore. Timing was critical. A delay of only a few seconds during loading could mean launching into heavier surf or colliding with nearby vessels. Once loaded, DUKWs entered crowded sea lanes filled with landing craft, debris, and floating obstacles left by earlier waves of the invasion. Drivers had to navigate narrow approach paths while maintaining enough speed to remain stable in the water. Stopping was rarely an option. A stationary vehicle risked being pushed sideways by waves or struck by another craft. Communication between naval crews and drivers relied on hand signals and shouted instructions, creating moments of confusion that could quickly become dangerous. Points while avoiding craters, anti-tank points while avoiding craters, anti-tank obstacles, and damaged landing craft. If a vehicle stalled while climbing out of the water, waves could strike from behind, forcing water into the hull or pushing it back toward the deeper surf. Crews frequently relied on momentum and careful throttle control to transition from water to land without becoming trapped. The absence of permanent infrastructure forced engineers to improvise solutions. Temporary causeways, floating piers, and artificial harbors were constructed to reduce dependence on open beaches, but these systems required time to assemble and were vulnerable to storms and enemy action. Until such structures became operational, amphibious trucks formed the backbone of supply delivery. Each trip represented a calculated risk, balancing the urgency of resupply against the dangers of repeated exposure to rough conditions. Enemy fire added another layer of complexity. Even after initial beachheads were secured, German artillery and aircraft targeted supply routes whenever possible. DUKWs moving across open water or unloading at the shoreline were visible targets. Drivers often operated without armor protection, relying on speed and timing rather than defensive capability. Damage to a single vehicle could block narrow access points, delaying the flow of supplies to advancing units. Weather remained an unpredictable enemy. Sudden storms or rising winds could halt operations entirely, leaving troops inland waiting for essential resources. The famous Channel Storm in June 1944 demonstrated how quickly logistical systems could be disrupted. Rough seas damaged artificial harbor components and increased losses among amphibious vehicles attempting to continue deliveries. Commanders had to decide whether to risk sending DUKWs into worsening conditions or accept delays that might slow the advance. Required constant inspection. Hull seams required constant inspection. Hull seams needed reinforcement, and bilge pumps had to function perfectly to prevent flooding. The success of beach logistics depended not only on drivers and planners, but also on mechanics working long hours to repair damage between missions. Despite these dangers, the ability to supply armies without ports changed the tempo of the campaign. Troops advancing inland received resources faster than German planners expected, allowing Allied forces to maintain pressure even when infrastructure remained damaged or contested. The DUKW did not eliminate logistical challenges, but it reduced the time between arrival offshore and delivery on land, creating a more flexible supply chain during the most vulnerable phase of amphibious operations. Behind every crate delivered stood a complex system defined by risk and improvisation. Beach operations required coordination between naval crews, drivers, engineers, and frontline commanders, all working in an environment where small mistakes could lead to loss of life or critical equipment. Supplying armies without ports demanded more than innovation. It demanded endurance, adaptability, and a willingness to operate at the edge of what machinery and crews could safely accomplish under wartime pressure. Accidents, loss reports, and the tactical debate over depending on the DUKW. As amphibious operations expanded across Europe, the DUKW amphibious truck became an essential part of Allied logistics, Yet, behind its reputation for versatility was a steady stream of accident reports, mechanical failures, and operational losses that forced commanders to question how heavily they should rely on a vehicle operating at the limits of both land and sea capability. The debate was not about whether the DUKW worked. It was about whether its risks were acceptable in sustained combat conditions. Loss reports revealed patterns that concerned planners. Many incidents did not occur during direct enemy engagement, but during routine crossings in rough weather or crowded landing zones. Capsizing in heavy surf, hull breaches from submerged obstacles, and engine failures far from shore accounted for a significant portion of damaged or lost vehicles. These accidents highlighted a central weakness. The DUKW's effectiveness depended heavily on environmental conditions, leaving little margin for error when seas became unpredictable. Commanders studied these reports closely, especially after operations where multiple vehicles were lost in a short period. Some argued that reliance on amphibious trucks created a false sense of logistical security. When conditions were favorable, supplies moved quickly and efficiently. When storms arrived or surf intensified, the same system slowed dramatically or halted altogether. Critics within Allied planning staffs suggested that more traditional landing craft, despite being slower to unload, offered greater stability in rough seas. Mechanical reliability became another point of discussion. Continuous exposure to salt water accelerated corrosion and wear on critical components. Even minor leaks could escalate into serious problems if bilge pumps failed or cargo weight exceeded safe limits. Maintenance crews reported increasing workloads as campaigns continued, raising concerns that sustained reliance on the DUKW might reduce long-term operational readiness. Engineers recommended stricter inspection schedules, but the pace of wartime logistics often made extended downtime impractical. Crew safety added urgency to the debate. Unlike armored vehicles, the DUKW offered limited protection against enemy fire or environmental hazards. Drivers and cargo handlers were exposed to waves, cold water, and flying debris during loading and unloading. Rescue operations for overturned vehicles were dangerous, particularly in rough surf where visibility was poor and currents strong. Some commanders questioned whether the benefits of rapid supply delivery justified the risk to personnel operating under such conditions. Supporters of the vehicle countered with operational data. They pointed out that without amphibious trucks, the volume of supplies reaching advancing troops would have been significantly reduced during the early phases of major landings. The DUKW allowed cargo to bypass damaged ports and congested beaches, delivering materials directly to inland points where they were urgently needed. From this perspective, accidents represented the unavoidable cost of maintaining momentum during complex amphibious campaigns. The tactical debate extended beyond engineering concerns into broader strategic thinking. Allied planners weighed flexibility against reliability. Amphibious trucks offered speed and adaptability, but required careful coordination and favorable conditions. Traditional landing craft provided greater stability, but slowed the transition of supplies from sea to land. Some commanders advocated a mixed approach, combining both systems to reduce dependence on any single method. Others believed that refining training and loading procedures would minimize risks enough to justify continued heavy use of the DUKW. In the end, the tactical discussion surrounding the DUKW reflected the broader reality of wartime innovation. Commanders were forced to rely on imperfect tools because perfect solutions did not exist. Accident reports and loss statistics did not signal failure. They represented the cost of maintaining supply lines in an environment where traditional infrastructure had been destroyed or rendered unusable. The amphibious truck became both a symbol of logistical ingenuity and a reminder that every technological advantage carried its own set of risks, forcing leaders to balance necessity against the limits of machinery and human endurance.